Okay, let's start chapter 2 with charge, motion, and constant and uniform electromagnetic fields. In this chapter, we will suppose that the electric field and the magnetic field are prescribed and they are not affected by the charges. That is, they are constant and uniform. That will be a not very realistic situation, but it's easier to understand the motion of charges in electromagnetic fields. The equation of motion that we will use for charges is an equation of motion will be this one with the Lorentz force moving the particles. Q is the charge, V is the particle velocity cross B. Okay, this is equation 1.1. Here P is the momentum, which is the Lorentz factor times the mass times velocity. The Lorentz factor is, 1 minus v squared over c squared, where c is the speed of light, to minus 1/2. But we'll consider that the velocities are much smaller than the speed of light, so we'll use gamma equal to 1. Okay, in this case, we have constant mass. We are not considering relativistic effects here. We can write the equation this way. Charge times E plus V cross B. That's equation 1.2. The equation numbers here in my class notes usually will not be equal to the numbers in the book. So this is 1.2. Sometimes, most times, maybe they'll be the same. So, but sometimes they're not. So let's talk about conservation of energy. So this would be the introduction to the chapter. Then there is a second section 2 of the chapter 2 of Bittencourt's book. It's on energy conservation. And we'll start then with, sorry, I'm writing in Portuguese. We'll start with E equal to 0, no electric field, no background electric field, and a background constant magnetic field. Okay? In this case, we have 0 in this equation, so the equation of motion will be dv dt equal to q v cross b. This is equation 2.1. Okay, then we'll multiply this equation by v, or actually do the dot product with v. So if we do it, we have dv dt dot v in this side and the same in the other side dot v. Then here we know that v cross b is perpendicular to v, but then if you do a scalar product with v, perpendicular to v, scalar v, it has to be 0, right? So this is, since V cross B is perpendicular to V. So this is equation 2.2. Is it? This is 2.1. Yeah, 2.1, 2.2. Now we can rewrite this equation this way. Notice that, but if you have dv dot v dv dt, this can be written, if you adopt v is a vector with three components, vx, vy, vz. Okay, so this can be written in this way: dvx dt times vx, because of this, plus dvy dt times vy plus dvz, this is a z, dt times vz, right? And you have, well, v square is equal to v dot v, which is vx square plus vy square plus vz square. Well, in this case, if you derive v square dt, what do you get? You get 2 times this times the derivative of this with t, right? So it's 2 vx dvx dt plus 2 vy dvy dt plus 2 vz dvz dt. Okay, so we see that this can be written, if you take equation 2.2, 2.2 can be written as d dt 1/2 mv square equal to 0, right? I just rewrote this dvt times cross, dot dv based on the comparison of this equation with this one. So I can rewrite this as this. Just have to add this multiplication by m and divide by 1/2 because of this 2 and difference with this. Okay, so this is the new equation, equation 2.3. It shows you that kinetic energy is conserved. This is an important result. If you have no electric field and constant magnetic field, then the kinetic energy of the charges will be conserved. So static magnetic field does not change kinetic energy. Notice as well that B had to be constant in order to have a zero electric field, because if observation, if B is different from a constant, then you have from Faraday-Henry's law, the curl of E is equal to minus B del T, right? So if the magnetic field changes with time, you cannot have a zero electric field because of this equation, right? So this is different from zero. So we will not consider a situation where this is different from constant and this is equal to zero. This is impossible. So no need for us to test that hypothesis. The second situation is if B is equal to constant and also the electric field is constant. Then the motion, equation of motion will be dv dt equal to q times electric field plus, just repeating equation 1.2 here. Then we know we can multiply this by v, and we end up with dv again, dot product with scalar product with v, q, exactly the same thing I did before, but now since I have an electric field, I can drop this term, but I cannot drop this one. So we end up with this equation, 1/2 mv square equal to q electric field times, dot v. This is 2.4. So what 2.4 is telling us is that the electric field does change the kinetic energy of your system. If you use the electric field equal to minus the gradient of the potential, electrostatic potential, then you can write this equation as d dt to 1/2 mv square equals minus q, the gradient of phi, times v. So I just change this here. And well, this is v. V is just the derivative of space with time. So we can write minus q nabla phi dot dr dt. R is the position vector. So, and this can be written in a shorter way like this. Why? Because d phi dt, by the chain rule, this is a function of r of t, right? The potential is a function of position, and position is a function of time. So by the chain rule, this derivative with time is the derivative with r, which is this, times the derivative of the argument with t. So this is just a chain rule, right? Okay, so we have just moved this part to the left side. You can write d dt is equal to 1/2 mv square plus q phi. This is equal to 0, right? So 2.5, and it shows us that the sum of kinetic energy with potential energy is a constant when you have static electromagnetic fields. Okay. Another observation here. Why can we use, how do we know we can use this form for the electric field? It's minus nabla phi. Well, we can use it. We can use E equal to minus nabla phi because d del B del T is equal to 0, because we have chosen a constant magnetic field. So if we had used a non-constant magnetic field, then we wouldn't have this relation. This implies that this is right. So with the curl of E has to be 0 if you have a constant magnetic field. With nabla phi, we have this situation because the curl of the gradient is always 0. So this is actually null vector, right? So this is satisfied because we have a constant field, so the curl of E is equal to 0, so everything is consistent here. Our third situation will be an electrostatic uniform field, so we will have no background magnetic field and a constant electric field. So equation 1.1 will become dp dt equals QE. So this is this equation, so this is 0. So this is 3.1. This is not a difficult equation to solve because E is constant, so these are separable variables. We can just multiply dt in both sides, so we have QE dt. Then we can integrate it, so we have integral here, then we'll have a constant of integration. Since the equation is on P, the constant we'll call P naught, okay? It's actually a vector of constants. Okay, then the integral of dp will be P. This is constant, this is also constant, so we have QE t plus P naught. P is just mass times velocity. And velocity is just mass times, well, velocity is dr dt. And we can actually integrate it once more to obtain the position. So the position, if we integrate this, well, let's multiply again by dt. We have dr equals QE t dt plus this constant vector times dt, and we'll integrate again. The equations have separable variables, we can just integrate them. And there will be another constant vector of integration, integrating constant here. So since the equation is on R, I'll call this, this is could be just a C0 for instance, but I'll call C0 Rm, R0m. Because if you add initial conditions to it, you will see that this is the right choice of constant of integration. So this is a constant vector times the mass. Then we have mr equals QE, this is t squared over 2 plus P P0 t plus this is actually not a dot, this is a 0 plus this and what else? But P naught is actually just mass times velocity times t, right? So we can rewrite this equation like this, dividing by mass. R is equal to 1 over 2 QE over m t squared plus V naught t plus R naught. Okay, this is 3.2. You can see that QE over m is causing acceleration in the particle. Why am I saying this? Because of equation 3.1. Because here we have mass times velocity is the momentum, right? So you have dv dt is equal to QE over m. So this is actually an acceleration. QE over m is an acceleration. See, what is the equation? 3.1. 3.1. If Q is larger than 0, the particle will accelerate in the direction and sense of E. So it's the same direction as E. Particle accelerate. Particles accelerate in the direction of E. If Q is more than 0, then particles accelerate in the direction of minus E, opposite direction. And there is no acceleration perpendicular to E. Okay? So this is simple motion in the direction of the electric field. Okay, now let's go back to the first case where we had 0 electric field and constant magnetic field. We had previously concluded that there is conservation of kinetic energy if you don't have electric field. So if you have electric field, then you have acceleration of particles, but if you don't have it, you don't have acceleration. You do have conservation of kinetic energy. But let's try to solve the equation of motion formally in order to see what is the motion of the charges, how they look like. So this is the equation of motion when you have E equal to 0. Oh, this is equation 4.1. And in order to understand the motion of charges, we will adopt this decomposition of V into a parallel component plus a perpendicular component, where a parallel component is parallel to the background magnetic field. Remember, it's constant and it's uniform. So it's a parallel component, and the perpendicular is a component on a plane perpendicular to B. So this is the velocity field, velocity vector. It's decomposition into these two components. All right. In this case, if you use this into equation 4, we can write the equation of motion with two components. It will be dv parallel dt plus m dv perp dt equal to q times v parallel cross b plus v perp cross b. Well, we know that if V parallel is parallel to B, then the cross product here will be 0. Okay. Then we end up only with this component, the perpendicular component. So we have this. We have m dv parallel dt equal to 0. that in the book I think it's 4.4. And in the perpendicular component is this QV perp cross B. Right, if you sum these two equations, you get this one. So you have V perp cross B. Where is it? It's perpendicular to both V perp and to B, so it has to be on the plane perpendicular to B. So V perp cross B is part of the equation for the perpendicular component of the acceleration dv dt. So that's why I have kept it here. This is 4.5. Well, from 4.4 we see that the velocity of particles along B does not change, so it's a constant velocity. Now let's rewrite equation 4.5 in this way. Let's change the notation in order to make it easier for us to interpret what is happening. So rewriting equation 4.5. Let's write it like dv dt. Well, we have it like this, B cross V perp. This is just like here, right there. Yeah, I haven't changed anything, just divided by M. Let me just put it in the right place here. We don't usually divide, okay, like this. And I will introduce this notation. I'll call minus QB over M. I'll say that it is omega C, the vector, cross V perp. Okay. Where omega C, this vector, is equal to minus QB over M. And this can be written like this. The modulus of the charge times B, the modulus of the magnetic field, over M, times this vector, unit vector. And I can write it this way. Okay, 4.7. I just introduced a new notation where this is equal to the modulus of this. So based on the sign of this equation, of this relation, we see that this unit vector omega c points in the direction of B for Q less than 0. Q more than 0, then you have it because of this minus here, so it has to have a negative Q in order to have the same direction of B. And omega C points in the opposite direction. For Q larger than 0. Well, we have already deduced in the previous, in the beginning of this class, that the kinetic energy is conserved in this case. So since the energy is conserved, we know that the modulus of v perp is conserved as well. Why? Well, because you have a constant v square, right? V square is constant. And v square is just this. It's constant. I should not write CT because you may think that CT is a C times T and T is time. No, that's not the case. It's just like this, right? Okay, so v square equals this, and this is constant because we have conservation of kinetic energy. But we also have v perp constant. Right, because of 4.4, where is it? 4.4 here. V parallel is constant. Remember, when I'm not drawing the arrows on top of it, then this is the modulus of the vector. So this is constant. So if this is constant and this is constant, then this has to be constant. So this is it, right? It's due to conservation of kinetic energy. All right. Then what else can we say? But 4.6 shows that v perp is not constant. You see, you have an equation for it. So the modulus is conserved, it is constant, but the vector itself, and this should have a vector here, sorry. So this is changing, v is changing, v perp is changing, but its modulus is conserved. 4.6 shows that v perp is not constant. And the acceleration is perpendicular to both v perp and to b, because you have here, this is the acceleration, the perpendicular acceleration. It has to be perpendicular to both b and v because it's given by the cross product between b and v. So is not constant, and it is perpendicular to b and v. Oh, sorry, it's acceleration. This is wrong. And its acceleration is perpendicular to b and v. Thus, the acceleration produces what? It's a rotation of v perp on the plane perpendicular to b with a certain velocity. So why? Because if you have, look at this, if you have a vector v perp that will not have its modulus changing, but in itself it will be moving, and the acceleration is perpendicular to both this and this, so the acceleration has to be in this direction. So it will be moving, but it has to conserve the length. So it must be spinning. So it has to be rotating. And the rotation velocity, the angular velocity, is given by this omega vector. This is how I have written it here. Therefore, the acceleration produces rotation of v perp on the plane perpendicular to B with angular velocity, with angular velocity omega c, also constant. So using v perp equal to drc dt in 4.6, where is it here? So instead of dv, I'll write dr dt. No, sorry, here dr dt. So we'll mix both notations, so it'll be dv perp equal to omega c vector times drc dt, and this is dv dt. I'll multiply it by dt, and this will cancel here, and integrate. This will produce v perp equal to omega c. Because this is constant, it can go out of the integral. So vc times, or cross product with rc. And this is because it had just dr, so you got r. And this is a function of time, this is a function of time, plus some constant, integrating constant vector. If you had as your initial condition a particle that was already in rotating motion surrounding B, then this constant can be made equal to 0. So let's choose, if C1 equal to 0, let's choose this equal to 0. drc dt. This is just the perpendicular velocity. I'm calling drc dt is equal to omega c rc. And this is 4.8. You see, RC is a position vector with a relation to a certain point. It's a guiding center. So RC is a position vector. In relation to a point G, which is called guiding center. Okay. on the plane perpendicular to B. Now there's one curious thing here. We have the same equation for the velocity dr dt equals omega c cross rc is the same as for acceleration dv dt equals omega c cross v perp. Okay, so we can guess the motion of the charged particles by looking at this. So the velocity, the perpendicular velocity, is the omega c cross the RC. RC is, so we have two possibilities here. We have the angular velocity pointing in the opposite direction to B, and the angular velocity pointing in the same direction as B. So if you check our previous slides here, you have when Q is larger than 0, then the angular velocity points in the opposite direction. If Q is less than 0, then it's in the same direction. So that is exactly what we have here. And what is the perpendicular velocity in this case? Is it clockwise or counterclockwise? Well, the perpendicular velocity is omega cross r, so it's the cross product between omega and r. So if you move it like this, then you have it, the velocity resulting product would be in this direction, right? So you have this way. So you have it in the same direction of B, then the cross product omega cross RC would be going that direction, so you have counterclockwise. Okay. Well, this is just the perpendicular component of the velocity. So the perpendicular is clockwise or counterclockwise on the plane perpendicular to B. But the velocity is actually a combination of perpendicular plus parallel. So parallel motion is a constant along the B. So the resulting motion would be a helix, a helical motion in the clockwise or counterclockwise direction. So since V is equal to V perp plus V parallel, V is a helical motion. Okay, that's what constant magnetic field produces in your charges. We have a term given by pitch angle. What is pitch angle? Pitch angle or inclination angle is the angle between, it's the angle between B and V. That's what we call a pitch angle. And you have so from this decomposition we know that V cosine alpha is V without arrow, which means the modulus of V. V cosine alpha is equal to V parallel, and V sine alpha is equal to V perp. From here you get the pitch angle. Could be sine to minus 1 V perp over V, or if you prefer you may write it like this as well, TG arctangent of V perp over V parallel, V parallel. And V, if you square both sides and sum, you get V is equal to V perp square plus V parallel square. there's another term that we must identify a term here, which is, let me see, this one. So modulus of Q times modulus of B over M is what we call omega C, and omega C will be the cyclotron frequency or Larmor frequency. Omega C equal to this over M. This is equation 4.10. We'll use it later. This is the Larmor frequency, or also called cyclotron frequency. Or cyclotron frequency. So if you have an electron spinning around a magnetic field, we call it electron cyclotron frequency. No. And the radius, RC, equal to V perp over omega C, is our Larmor radius, or cyclotron radius. From equations 4.10 and 4.11, we can see that the larger B, the larger omega C, and the smaller RC. That is, if you increase B, you will have a larger omega C, and then you will have a smaller radius. Also, if you have larger mass, you have a smaller omega, and then you have a larger radius. That means that if you have an ion, ions are heavier than electrons, and you would have something like this. It's our positive charge. Positive charge means positive charge. Well, means that I have a clockwise motion for positive charge, but if you're looking with the magnetic field pointing toward your blackboard, then you would see something like a counterclockwise motion if you have B like this, right? Pointed toward the blackboard. This is for a positive ion. Ions have larger Larmor radius, and an electron would have a smaller Larmor radius and a clockwise motion if you look with B pointed toward the blackboard. In this view, it would be counterclockwise. Okay? And this is the guiding center, G. If you have trouble visualizing the motion, the helical motion of the charges in this uniform magnetic field, then you may want to read section 4.2 of the book, in which she has the solutions in a Cartesian coordinates. It's an example of solution where you have all the information you need to understand the helical motion. It's just basically the same thing I have shown, but with Cartesian coordinates. In section 4.3, magnetic moment is discussed. magnetic moment. Well, since we have a circular motion or helical motion, suppose that we have magnetic field pointing outward from the blackboard. Then for Q larger than 0, we would have in this view clockwise motion, right? Then we have the charge going in this clockwise direction. There is obviously a current here. This charge motion produces a current. Then associated to the current there is induced magnetic field in the sense opposite to B0 inside the circle. So, sorry, there is this, there is a magnetic field induced by the current here. Be associated to J. All right, so by Ampere's law, Ampere-Maxwell law, we have the curl of B is equal to M0J plus the displacement current, which usually well, in this case, you would have equal to 0 because we are considering that we don't have electric field. So that's the current. This is the current. In the case of a dipole let's try to draw this with more detail. So we have B not here, vertical direction. Then we have circular current. Then, well, I'm drawing this supposing that the parallel velocity is 0. Suppose the initial parallel velocity is 0, then we have just the circular motion. If we had the some parallel velocity, then it would be a helix. But now it's just a circular motion. We would have the induced field here all throughout this ring, right? Becoming a mess. So then we have a circular area A here. This is J is the ring current. And this is the dipole generated by J. So we have the circular ring here is, suppose it's a wire and it's followed by, the J is following the wire surrounding the area A. Barely can see an A here, okay? So a magnetic moment is produced and the absolute value of this magnetic moment is I times A. A is the area of the circular region surrounded by the wire, 4.26. And we have AI equal to the modulus of K, the modulus of Q over TC, where TC is equal to 2 pi over omega c, so this is like this. Tc is 2 pi over omega c. So this is the period of the orbital motion, or Larmor period. So M, the magnetic moment, this is magnetic moment. Don't confuse M arrow with mass. This is not mass, this is moment. And this is Q over omega C over 2 pi times A. A is pi r square, right? The area of the circle. We can write it like Q, just cutting this with this, Q omega C RC square. Well, we can write it using equations 4.10 and 4.11, where we define the Larmor radius and the Larmor frequency. So if you check from equations 4.10 and 4.11, where is it? 4.10, 4.0, oops, where is it? Well, 4.10 is this. So this is the Larmor frequency and this is the Larmor radius. So we can use those definitions in this formula for the magnetic moment and write it like this. The modulus of the magnetic moment is equal to 1/2 mv perp square over b. That's from here. And this we may call W perp over b. W perp is the part of the kinetic energy due to the V perp. Okay, so this is just this. If you, so this is how it is. And in vector form, the magnetic moment it has this expression. Use the vector here, like this, okay? So if you take the modulus of this, then it's a modulo of this, you cut with this, and you end up with this. Okay, I'll skip section 4.4, you may read it, okay? Read it. Don't skip it. I'm skipping it. You don't. You read it. I'm skipping it because I want to move forward to section 5, where we have electrostatic and magnetostatic, uniform magnetostatic and electrostatic fields. So here we're going to consider B equal to constant and E also equal to constant. Some constant fields. We have already dealt with this situation, but now let's try to do a formal solution of the equation of motion to understand what is happening with the charges in this case. So the equation of motion is dv dt equal to q times E plus Vb. Always this equation, 5.1. And we'll use V again, decomposed into two parts. And also for the electric field, we have a parallel component and a perpendicular component. These are parallel and perpendicular to B, so we don't have to decompose B like this. Actually, I should enlarge the screen like this. Okay. Okay, so this is electric field, this is velocity field. What shall we do with this? Insert that into equation 5.1, you end up with this. One component for parallel, one component for perpendicular is equal to QE parallel plus QE perpendicular plus Q parallel plus perpendicular for velocity cross B. Thus, well, we have already seen that M dV dt, well, it was actually 0 in the previous case, but now, well, this is 0, but not this one. We have the, for the parallel, we have still this term here, because now we have an electric field. So this is equation 5.2. And for the perpendicular component, we end up with a perpendicular field, the electric field, plus V cross B. Okay, this was 0 because this is parallel to this, and cross product will be 0. Okay. 5.3. 5.2 shows that there is an acceleration for the particle velocity. There's a change of particle velocity. This is an acceleration in the parallel direction. And the acceleration is constant. It is q times e parallel. So the acceleration in parallel direction is q e parallel over m. Acceleration is q e parallel over m. So it's parallel. So we are having acceleration in the direction of b. Just like in section 3, we have this equation for v equal to q parallel t over m. So I just integrated this. There will be a constant vector here, integrating vector. So just integrated with this equation. Sorry, not this one, this one. The parallel component equation. So this is it. And you may integrate it again. So this is dr dt. You integrate a second time. You will get t equal to 1/2 QE parallel t square over 2m plus v parallel 0 t plus r parallel of 0. Now we can try to solve. This was easy because it was this equation. Now we have to solve this one. To solve 5.3, we'll decompose v perp into two components. V perp will be equal to v perp prime of t plus ve, where ve is a constant velocity in the plane normal readable in the plane normal to B. Thus, V prime perp is the velocity observed in a frame moving with constant velocity VE. Okay. Now let's substitute 5.6 into 5.3, this one. Using 5.6 into 5.3, we get m dv per prime dt plus m dve dt, but ve is constant, so this is 0, which is equal to q times e perp plus v perp prime cross b plus ve cross b. Now let's write it this way, using E perp equal to minus E perp cross B over B square cross B. Now what is that? Why am I writing E like this, and how can I see it like this? Well, let's see. If you have B here and some vector E perp, then E perp cross B is going like this here, right? So it should be perpendicular to both, and in this direction. So if you have this cross that, is going like that, right? So this is E cross B cross B. Thus, I can write this like minus this, but divided by b squared. Why divided by b squared? Because if you take the modulus of this, it has almost the same modulus as this, but with the addition of b squared here. So we have to get rid of this one. You have to cancel this in the component of modulus. So, and you need the minus here to point it back towards this direction. But why have I written it like this? Because it's going to be easier to interpret the motion writing it this way. So let us see, I have this equation, right? Let's rewrite it with this notation. We have m dv perp prime dt is equal to q v perp prime plus ve minus e perp cross b over b square. Now we had, well, let me see. Yeah, we had b here, we have b here and b here. I can multiply everybody by b. I can do it like this, right? 5.8. Thus, if you choose VE equal to E cross B, if VE is equal to this, in this frame of reference, over v square, then this will cancel with this, and you have this. dv dt is equal to q v perp prime cross b. Okay, this is much easier to understand. This is the same equation of motion as the case where you had E equals the electric field equal to 0 and magnetic field equal to constant. This is the same as equation 4.1, right? Yeah, we ended up with equation 4.1. 4.1. So in the reference moving with the velocity VE, the electric field is eliminated and the magnetic field is unchanged. In this frame, the particle describes a circular motion with frequency, the cyclotron frequency omega c and Larmor radius rc. That is, we have, just like in the other section, we derived that the velocity would be like this. Okay, so it's a circular motion, but it's a circular motion in a reference moving with the velocity, the constant velocity VE. Thus, if we move back to the laboratory frame, this is in the moving frame, but in the laboratory frame, the particle motion is a circular motion on the plane normal to B, superposed by a uniform motion with velocity VE perpendicular to B and E perp, plus an acceleration, which is given by the parallel direction. Okay, so plus this one. So we're trying to describe the motion of V, which is V perpendicular plus V parallel from 5.4 and 5.6 and 5.10. Let me see, where is 5.10? 5.10 using 5.10 and VE from 5.4, 5.6, 5.10, and VE. Where is VE? VE per, no, just VE. VE is here. I didn't put a number in it. But VE, we have V equal to V parallel plus V perp, which is Q E parallel T over M plus V parallel not 0 plus omega C cross RC plus E B. Okay, this first term here is the acceleration and the constant acceleration of the guiding center along B. Constant acceleration of the guiding center along B. This is the velocity component parallel to B. Okay, initial velocity component parallel to B. This is the cyclotron motion. And this is drift velocity. We call it drift velocity of the guiding center. Perpendicular to both E perp and B. So how can we draw this motion or draft the motion in some easy way? Let's see. So we're trying to see what's happening with the charge. We have this term, which is this acceleration in B direction, cyclotron motion plus drift. So what happens? First, VE. VE is independent of mass and charge. It's a constant velocity, right? So it's the same for ions and for electrons. So VE is our plasma drift velocity. Since we have since E parallel cross B is equal to 0 because both are parallel to B, so the cross product is 0, then we can write VE, because where is VE? Where is VE? Here. So this is E perp cross B. But if instead of E perp we used E perp plus E parallel cross B, then that's E cross B. The parallel part will be 0, so it doesn't make any change. So we can write either E perp or E. So we'll write it like E, just because we can. So VE can be written like this as well. It's the same thing. E cross B over B squared. Since electrons and ions are moving in the same direction, because V is not dependent on the charge, we don't have a current. This velocity does not generate a current, because in the current you have charge times V, right? So it depends on the charge. So ions go one way and electrons go another way. So this is current. So this does not generate a current, because ions and electrons go in the same direction here. So basically, if we have, let's try to draw this. If I have magnetic field pointing out of the blackboard, then we have electrons going this way with a small Larmor radius. Electron this way, and we have ions going with a larger Larmor radius and clockwise, and this is counterclockwise. Then we have the perpendicular electric field like this. So this is E perp. Then E cross B would be like here, right? This is E cross B. Yeah, you move like this. Yeah, it goes this way. This is the right way. So we have circular motion plus a drift in this direction. So the ions would be moving like this. All right. and the electrons would be going the same direction, but with a motion like this. This is for negative charge, for positive charge. Of course, this is just part of the motion. This is this plus this. We still have to add an acceleration in the direction parallel to B. So we would have a motion in the direction outward from the blackboard. It's difficult to draw this here. So, but I think you got the basic idea. This acceleration parallel to B. Okay. Well, so this is not a current, but sometimes there may be a current in a situation like this if you consider collisions between charges and neutral particles. Then the frequency of collisions of ions with the neutrals is larger than the frequency of collisions of the electrons with the neutrals, because the ions are much larger than the electrons. So the ions will end up moving slower than the electrons in this case, generating a current normal to E and B, called the Hall current. But we'll study this in a future chapter. I'll leave section 5.2 for you. Read it. Now in section 6 we have an external force, drift due to external force. Okay, what happens here? So suppose you have an equation of motion like this. It's the same as always, E plus V cross B plus some external force. So we may write it like this: E plus F over Q plus V cross B. And to make things easier for us, let's consider that this is a constant force, constant vector field. So in following the same procedure as in section 5.1, but moving with the frame with Vf velocity instead of Ve, what is Vf? Let's do the following. F will be playing a key role here, similar to the role of the electric field in the previous example. So F will act similarly to E in the previous case. So it will produce an additional drift velocity. You can see this just repeating the previous analysis with this term, so it's basically the same thing. The drift velocity. Let's call this drift velocity Vf. So it's a drift due to F this time. So Q B square. This is in place of, let's see, what this one, right? But now there is this Q. It depends on the charge, because in this term I do have a charge in the denominator. So I didn't have it here, but now I do. So this drift velocity depends on Q. An example of an external force would be gravity. We can consider a uniform gravity field, and then you would have, instead of Vf, would be Vg with this configuration here. Okay, so you could think of other external forces. In this example, the drift has distinct directions because of the charge. So the behavior is similar to this one, but now the ions will go in one way and the electrons will go the opposite way. Basically, you would have gravity, magnetic field, gravity perpendicular to magnetic field, and then the electrons go in like this, negative charge, and the ions go in like this. This would be the G cross B drift. If you're considering that you have a constant electric field, then you have to add the motion due to E cross B as well. So I have to compose the motion with this. It's more difficult for me to draw it here. But I guess we have to take this one and add another drift. Since electrons and ions drift in opposite senses, now there is a current density. And the current density can be expressed like this. You have 1 over delta V. Then you're summing all the charges with the velocity Vgi. I is the index for each particle, each charge. And I can write this. This is just a mean current for a small volume of plasma. So we just sum everybody and divide by the volume. Then we have, let's see, well, Vgi is just, Vgi is given by this for each charge. So we have Qi Mi over Qi times G cross B over B square. I can cut this with this, and we end up with the mass density times G cross B over B square. So this is the current. Now this is working, we have the modulus of V, where is Vf? We're talking about Vf, the modulus of Vf is F, the perpendicular component of F. Why the perpendicular? Oh, okay, yeah, because this is just right. This is actually Vf F perp over QB. From equation 6.2, we see that, note that the modulus of Vf is equal to F perp over QB. If F perp over QB is much smaller than the speed of light, we can use equation of motion, non-relativistic equation of motion. as you have been doing. Okay, and this is the end of chapter 2.